We are going to look at the foundation of synthesis from a practice perspective. So the problems I'm going to use are Orgo 1, very similar to what I already have on my free worksheet. Just put worksheet in the comments and I'll give you a link. Yes, even if you're watching the recording. But we'll start with a warm-up question. You're given a molecule. You're asked somehow, some way to come up with this product. What is the first thing you're going to do? It is not to start thinking of all the reactions you know. You want to take a step back. As I covered in part 1 in the how to approach synthesis, we want to ask 2 very simple questions. One, the first reason is you want to kind of jumpstart your brain. You want to make sure that if you're blanking out, if you're forgetting, it gives you something to focus on. But also, you don't want to just rush right into the reactions and risk going down the wrong path. You want to make sure that you're actually going where you need to go. So question number 1, we want to see what is the same. And question number 2, we want to figure out what is different. And once we know exactly what we have to change, then we jump into the synthesis. So what is the same in this case is the entire, here we go, the entire chain, the entire molecule. I don't know why it's drawing this like I'm a drunk. Oh, because it's not plugged in and it was about to die. Hang on. Good thing I caught that. There we go. That should do it. So the entire carbon chain is the same. And what's different is that I have a pi bond on my starting molecule and I have a bromine on the product, which looks pretty easy. I just have to convert my pi bond into a bromine. The problem is, am I looking at a Markovnikov or anti-Markovnikov addition? Given that, if I number the molecule from the direction of the branch, I have 1, 2, 3, 4, 1, 2, 3, 4. The pi bond is between carbons 2 and 3. The bromine is on carbon 4. And this is numbered for the sake of having the reactant and product organized rather than we have to number it from the right or left. I don't care about that right now. So what I'm doing is I'm actually putting the bromine on a carbon that is different from where the pi bond is. And so we have to use the pattern. The first thing I want you to recognize is this is a move the functional group pattern, what we talked about in part 1. And anytime we want to move the functional group, when I say functional group, I mean anything that is on a molecule. The easiest way to do that is a series of elimination and addition, depending on what you're starting with. Since I'm starting with a pi bond, I know I want to move it in that general direction. The first thing I want to do is some kind of addition to give me a molecule that has a group that I can then eliminate. Addition, elimination, addition, elimination, and we step it along one by one. So what can I add? Let's add a bromine because why not? And then I can eliminate in the direction that I want to make sure I want to go. So we move the pi bond over one position, and then I do another addition, and very simple. I moved the bromine. Well, it's a different bromine, but I moved it over. And just to prove to you it's a different bromine, let's not even make that a bromine. Let's make that a chlorine. So now I have a pi bond, goes to a chlorine, goes to a different pi bond where I want it to move, goes to another bromine. And let's fill in the reagents. How do I go from a pi bond to a chlorine? Since the chlorine is on the less substituted carbon, I need an anti-Markovnikov addition. That means I'm going to use HCl, but using peroxides. This is the radical reaction. HCl and peroxides will put the chlorine on the less substituted carbon. Then I can eliminate it. And I want to make sure I do the elimination reaction that puts it again on the less substituted position. So this right here is an alkene reaction. Don't worry if you don't remember the exact specifics because I have different videos and I have my bootcamp that covers all of it. And so right now it's more the big picture. And then I'm making a note of which chapters you have to go back and review if something is not very clear. Once I have the chlorine, I want to do the elimination. I want to make sure I eliminate in the direction of the less substituted carbon. This is not going to be the Zaitsev product. It's going to be the Hoffman elimination. And Hoffman elimination means I require a big bulky base, something like tert butoxide, A tricky way to write it is KOTB in HOTB and heat. Let me explain what that is. K is simply a potassium. O is the oxygen. TB is tert-butyl. And the O is the oxide. We already mentioned that. This right here has a negative charge. This is a big bulky base, or I call it in some of my videos, chicken foot base. It is so big and bulky, it has to go to the less substituted position. It grabs the least substituted hydrogen, which is going to be the terminal one right here. And then I get my alkene. Once I have the alkene, I do another radical halogenation to get the anti-Markovnikov product. And that will be HBr and peroxides. And that's it. I move the functional group, or in this case, the bromine, over a couple of positions. So that was our warm-up question. Let me know if you are with me so far, if you need a little bit more time to warm up, or if you're ready to crank it up a notch. All right, how about something that looks like this? I have a starting molecule, and somehow, some way, I want to come up with a product that looks like this. What do you think? Easy, medium, or hard? And what is the first step? How do we get started for a problem like this? Well, the first thing we want to do is not start reacting. We want to take a step back and evaluate what we're going to do here. So question number one, what is the same? And question number two, what is different? What is the same is just the cyclohexane. We have a 6-carbon ring. And what is different is everything else. We're adding 2 carbons plus an alcohol. What reaction do you know that will add 2 carbons and an alcohol? And since we have Orgo 1 and Orgo 2 students here, let's do this 2 different ways. Let's do the Orgo 1 version, and then we'll do the Orgo 2 version. We can add any reagents, anything else that we want. Before starting a reaction like this and starting to figure out what it is I'm going to add, the question I have to consider is, how am I going to add it? Where am I going to add it? I have nothing on this molecule. I can't substitute, I can't eliminate, I can't attack, I can do nothing. So the first thing I have to do is recognize that I have another pattern here. And the pattern that I have here is the something from nothing. When I have the something from nothing, it means I have nothing on the ring that I can react with. Give me a halogen and I can do anything with it. I can substitute, I can eliminate, I can attack, I can turn it into a grenade, whatever I want. But if I have nothing, then the first thing I need to do is make this molecule reactive. So without even worrying about how I'm going to add all of that, I'm going to start with a simple radical halogenation to get me some kind of leaving group on this molecule. Whoops. Now that I have a leaving group on this molecule, bromine is a good go-to. Radical halogenation will put a bromine on the most substituted, the most stable radical intermediate, therefore the most substituted carbon. And then I can think about what to add here. We'll start with the Orgo 1 reaction. What reaction do you know in Orgo 1 that will add a carbon chain that will elongate your chain onto a molecule that has a good leaving group? There's only one reaction, and that is the acetylide, meaning we use an alkyne for chain elongation. And so I don't even have to consider this yet. All I have to worry about first is the fact that I'm adding 2 carbons. So I have an option of moving forward with a couple of steps that I know, or I can work backwards. That was meant to be an arrow. I can work backwards and say, going one step back, if I know that the only way to grow this chain is with an alkyne, then how could this have come from an alkyne? It had to somehow, some way come from an alkyne. I don't know why my arrows keep winding up drunk. If this had to come from an alkyne, I don't know how to go straight from an alkyne to the alcohol. So instead of getting stuck, because let me know in the comments if that happens to you, if instead of getting stuck along the way, let's just say that I know some way this had to come from an alkyne, but I don't yet know the exact reaction. So let me draw the alkyne that I know it came from and then treat it like multiple problems. This alkyne has to add carbons 1 and carbon 2. That is it. So that is my new bond. And here are the 2 carbons that I'm adding. I know that this is where I'm going. And now I can treat this almost like 2 different problems. Francisco, for the Orgo 2 version, we're going to go there. Absolutely. But right now I'm first covering Orgo 1, where many students have not learned the organometallics. And so in this case, I can actually go directly from the halogen to the alkyne by a simple SN2 reaction. So we'll hold on to that. And then from the alkyne to the alcohol, I don't know how to do that. So to go straight from here, not possible. So I ask myself a different question. If I don't know how to go from the alkyne to the alcohol, is there another molecule that I know along the way? Any other molecule that maybe kind of resembles something like an alkyne that would have given me an alcohol at the primary position? Why, yes, I can use an alkene. I know that if I have an alkene that looks very similar to this alkyne, this is the new bond, the 2 carbons that I added on, but now they are at 120 degrees because they're sp2 hybridized. If I have this alkene, I can do an Antimarkovnikov hydration. That'll put an alcohol on the primary position. And so now I have to ask a different question. Can I go from the alkyne to the alkene? And the answer is absolutely yes. And that's it. I start with my chain, I add a bromine, I do a substitution reaction, I partially reduce it, I turn it into an alcohol. I am good to go. So now that I'm happy with my intermediates, I can go back and start filling in the reagents. To get that bromine on there, I'm going to use Br2 in heat and light. Heat or light, either one will work. This will give me the radical halogenation. This is a radical reaction. We already mentioned that this right here is an SN2. Specifically, what I'm going to use is a deprotonated alkyne, in this case, the acetylide anion. I'm using Na as a counter. This will be my SN2 attack, like this, kick out the bromine. Once I have the alkyne, to go to the alkene, I need a partial reduction. I need it to stop at the alkene rather than going all the way. This right here is a redox reaction. Depending on your professor, it'll show up in different chapters. This may also show up in your alkene or alkyne chapter, probably alkyne. I'll just put or alkyne in case you're trying to figure out which chapter to review. I can do this with 2 different reagents because the molecule is terminal. Notice that I have a hydrogen here. I have 2 hydrogens here. So it doesn't matter if I use a cis-promoting or trans-promoting reaction. Because it's terminal, it doesn't matter. So let's go ahead and use H2 with a Lindlar's catalyst. That will give me an alkene. If this was internal, it would have given me a cis alkene, but here it doesn't matter. And finally, to get that primary alcohol, I need the Antimarkovnikov hydration reaction. That will be hydroboration using BH3 in THF as step 1. Step 2, NaOH and H2O2. Kind of running out of room, so I'll just make a note here. This is the alkene chapter. And there we go. From our starting cyclohexane all the way to the substituent with an alcohol on it. If you're with me so far, let me see a couple of fire emojis in the comments. And then we'll jump on over and do this Orgo 2 style. So let's see a completely different pattern, a completely different approach that we can take if we have more reactions available to us. If you joined late, welcome. I'm happy to have you here, and you're able to catch up on the rest later. You don't have to worry about typing or about copying all the notes or drawing everything out. I will save this as a PDF. Just put live notes in the comments, and I will give you a link to access the notes. Yes, even if you're watching the recording. The problems that I'm doing are very similar to the practice problems I have on my free synthesis worksheet practice exam that is not available on my website. Just put worksheet in the comments and I will give you a link for that. And since we're talking about links, I also have a brand new organic chemistry pre-finals assessment. It is basically a beast of an exam that goes through every topic from chapter 1 all the way through synthesis and retrosynthesis like we're doing today. And because it's organized in order, it's a very good way for you to ask yourself, am I ready for my Orgo 1 final? You take the assessment, you figure out which topics you're strong in, which ones are weak in, and you have to go back and review, and then you know how to split your time for finals. So the entire pre-finals assessment is not free, but I have a sampler, 15 questions that go through a good representative group of topics, and you can get that as well. Just put final in the comments so I know that you're looking for that separate from the synthesis worksheet. I'll give you all those links. In the meantime, I was trying to draw a molecule and talk at the same time. That didn't quite work out. Let's see if there is a completely different route that we can go to solve this. If I'm not limited to just Orgo 1, and I'm not limited to just the acetylide anion, an alkyne to grow the chain, I can use anything. And my go-to for chain elongation in Orgo 2 is the Grignard. The Grignard is so versatile. It attacks everything. It gives me so many different options that is always the first thing I think of. And with the Grignard, there are a couple of patterns that you can look out for. And this right here is a very, very easy to recognize pattern. Anytime you notice that you have 2 carbons on your molecule, where those 2 carbons have as follows: carbon number 1 and carbon number 2. If carbon 1 has an alcohol or something that could have come from an alcohol, maybe you oxidized it, maybe you eliminated it, and carbon 2 has a new group, then I want you to immediately recognize that this right here was a Grignard attacking an epoxide. This right here came from the Grignard attacking the epoxide. And as soon as you see that, you know exactly what to do. Well, first we need a Grignard, which means we need a halogen, which means we need to start with a something from nothing reaction because I have nothing on the molecule. So what do? We'll react it with Br2, heat and light, as we did before. So for heat, you'll typically see a triangle. For light, you might see this representing some kind of wavelength, or h nu, to show that there's a wavelength coming at it. This will give me a bromine, which I can then react with magnesium to give me a Grignard. The magnesium will insert itself between itself and the bromine. And now all we need is that epoxide. So that's it. That's way, way fewer steps using the Grignard. And all I have to do is step 1, an epoxide, and step 2, I'm going to have to add some acid just to protonate it. So which chapters are we looking at? This one right here is the radical chapter. This one right here is the Grignard. I don't know if you have a separate one or under something else. I know in my book it was a carbon-to-carbon bond chapter. A lot of students learn this in the alcohol chapter, so I'm just going to put Grignard, and you can find where your professor covered it. And then over here, this is either the epoxide chapter or Grignards, again, depending on where it comes up. Usually alcohols, ethers, epoxides is what you have to review. And that's it. That is our reaction. Francisco, let me know if this is what you were thinking and if this feels so much easier compared to what we were doing before. So let's switch gears. If you're with me so far and you want to crank it up a notch, I'm going to show you the next problem, and I want you to let me know if this looks easy, medium, or hard. 1, 2, 3, 4. 1, 2, 3. That has to be drawn differently. Like that. Okay. Somehow, some way, we need to come up with the synthesis pathway that will give me this right here. What do you think? Easy, medium, or hard? So the first thing we have to do is ask the questions. Question 1, what is the same? And question 2, what is different? What is the same is nearly everything. We have the same number of carbons, we have a pi bond. What is different is we added 1 pi bond onto the molecule. What reaction do you know that will take an alkene and add 1 pi bond to make an alkyne? See, it looks like an easy question, except I don't know of such a reaction. I have been doing organic chemistry for a very long time, so unless they discovered something new, this is not possible. And if I cannot make my product from my reactant, this is where a lot of students panic, and I'm going to challenge you, don't. Get rid of your starting molecule and ask a completely different question. If I can't create the product from my starting molecule, is there a different molecule I can use to create this product? Is there something else that I can start with that will give me an alkyne? Why, yes, there is. If I have a molecule with, say, 2 halogens, I can do a double elimination, and that will give me the alkyne. I didn't start with my starting molecule. I started with something else, and I know that this will go to where I need it to go. And then I ask the question again. Is there a reaction that will take my alkene and give me a double halogen on it? Why, yes, there is. That is a very simple reaction. It is just alkene halogenation, and that's it. So this right here is an alkene reaction. This one right here is in the alkyne chapter, an alkyne reaction. All we have to do is fill in the reagents. So if this looked hard, this is actually a pretty easy question. Let's move this over so I have room to write. What are the reagents to carry out this reaction? To go from the alkene to the dihalide, I will simply need a dihalide like Br2. And we don't want a radical reaction, so we put it in an inert solvent like CCl4. Then, if I have my dihalide and I want the alkyne, this is where it gets a little tricky. It's a 2-step reaction. Step 1 is my double elimination using something like NaNH2 and NH3. But then step 2, I have to add water. And let me show you why. Because it doesn't look like you're doing anything different, but it makes a big, big difference. If I have this molecule and I have a bromine here and a hydrogen, I have a bromine here, a hydrogen here, and another hydrogen here. So these are the atoms that are involved in this reaction. If I react this with NaNH2, I'm not reacting with 1 molar or 1 equivalent because these molecules will attack no matter what. And if I put a limited amount, some molecules will react multiple times, some will not react at all. It's like putting out candy and saying, everyone grab one. No, some kids are going to grab 3. It's the way that it is, right? And so the first NH2 minus will show in green. We'll grab the green hydrogen, eliminate the green bromine. The second NH2 minus will show in light blue because it will grab the blue one, eliminate like that. And it gives us the product that we expect. It's the product that we want, where we have the green pi bond forming and the light blue pi bond forming. Let me change the color of the parent chain so the difference is a little more obvious. Like that. Okay, so this is what we expected to form. The problem is I still have NH2 minus in solution. And that gray hydrogen is not going to be allowed to stay there. Another NH2 minus is going to come and grab that hydrogen, give it back its electrons, and I am left with a deprotonated, somewhat quite reactive alkyne, a good nucleophile for an SN2 reaction, which is great if my next step is a chain elongation, meaning if I bring in an alkyl halide where I want to kick something out. But in this case, because it's not what I want, the next step is to bring in water, because water is going to get attacked for a proton. That proton will be plucked off of water, and then you're forming an OH minus in solution, which is not as strong a base compared to the alkyne. And that is why we need that extra step here to give us that extra hydrogen there. And now we're good. So let me know if you're with me so far. Let's see which question we're going to do next. What do you think for the next question? Something easy, medium, or hard? Let's go. I wonder if this is too tricky for an Orgo 1 question. Well, let's go with it. All right, I see a request for hard. Are you an Orgo 1 or 2? Because we can solve this both ways. So let's go for it. What's my first step? Where? Oh, Brian, this is anything but easy. But hey, let's give it a shot. How do I begin? Where do I go with a problem like this? Question 1, what's the same? Question 2, what is different? We'll start with the Orgo 1 option, which is using the alkyne for chain elongation, but I'm jumping ahead of myself. What is the same? This ring right here. What is different? Just that ring. What is different is that I'm adding an alcohol and, well, I have an alcohol, so I'm technically, am I adding an alcohol? Let's see what's going on. It's the ring plus the alcohol, and then I'm adding plus 2 carbons. What reaction do you know that will take a molecule and just squeeze in 2 carbons without changing the alcohol, without interfering with what is already there? If you are thinking you don't know of such a reaction, you are absolutely correct, because there is no reaction that I know of that will simply pluck out a hydrogen and turn it into something else. And if that's the case, you have to think of it differently. Instead of thinking of this as an alcohol that is still there, ask yourself, what reaction do I know that can add carbon to a molecule and then somehow, some way later, add an alcohol there? If you think of it that way, now we're just looking at this as a chain elongation and then trying to figure out how to put an alcohol there maybe after the fact. If that's how I'm thinking of it, then somehow, some way, for the Orgo 1 version first, I know that this will have at some point been an alkyne that added onto a molecule where this right here is my new bond, and here is the alkyne. And it should really be drawn linear because the alkyne is sp hybridized. So we'll draw it like this, actually connected. And somehow, some way, I will then get an alcohol on this position. But let's hold that thought. And let's see if we can think of a route to go from that starting alcohol, unrelated to the ending alcohol, and get the alkyne on there. I don't know how to do that. There are too many things going on. But I know that to get the alkyne on there, one step back, I would have had to have a leaving group on the molecule, for example, chlorine. I like drawing bromines, but we could do chlorine just as well. And then an SN2 reaction will put the alkyne there, which brings up a new question. Do I know how to go from an alcohol to a chlorine? Yes, I do. Just turn the alcohol into a good leaving group. So that will be, let me give myself a little more room on the further side. Whoops. So once I have that leaving group, I can put the alkyne there. Now I'm coming back to this portion of the molecule. How do I go from an alkyne on substituent carbons 1 and 2? I could have numbered it the other way, doesn't matter. to an alcohol here. I don't know how to do that, but I do know that if I do anything to the alkyne, the reactivity will be either here or here, which means I need that addition elimination move the position of reactivity, reaction, which was a series of alkene addition and elimination. So I need to turn this into an alkene, allowing me to have something that I can play with, something that I can move. If I turn this into an alkene, I can put something here and then move it over. So let's go ahead and do that first. What if I put, I'm just going to change this whole thing to purple now because it'll be easier. What if I put something like a bromine here? Then I just have to move the reactivity over and put an alcohol there. So what can I do? I can eliminate it. And if I eliminate that bromine in the direction of where I want to go, then I get an alkene here. And from here, I can just do an alcohol, just a hydration reaction, and I'm good to go. That is it. Did this turn out to be easier or harder than what you first envisioned when you saw it? Yes, even if you're watching the recording, let me know in the comments. Call this the alcohol question so I know which one you're talking about. Sometimes students will leave comments and say it was harder, and I'm thinking, okay, that was an hour-long session. Which reaction were you talking about? So let's go and fill it in. The first reaction is under SN2 or the alcohol chapter. You would have learned it under both. I'll just put or. And what I want to use here is something that'll turn the alcohol into a good leaving group. Because it's secondary, I have multiple options. I can even do something like HCl. That in itself is good enough. But I think professors are looking for something a little more advanced like SOCl2 in pyridine. That will turn alcohol into a good leaving group by giving it a big, bulky, resonance stabilized leaving group. Once I have the chlorine there, I bring in the acetylide anion. So I will bring it with an Na and then C, triple CH like that. That's my SN2 reaction. A little more room here. Here we go. That's SN2. Once I have the alkyne, I want to get to an alkene. That'll be a reduction. I've shown you the Lindlar before. This is terminal again, so we can use either one. So we'll use sodium in liquid ammonia. Again, it doesn't matter because it's terminal, but I want to show you both. Once I have the alkene, I want the bromine on the more substituted carbon. I just tricked myself. That is not the case. This is a trick question. This will not happen the way I envisioned it, and let me show you. If I take this structure right here, and I try to do a Markovnikov halogenation reaction, watch what happens. If I take this right here, and I react it with HBr, I have the pi bond grabs the hydrogen, bromine breaks away. I get a carbocation intermediate. Whoops. I get a carbocation intermediate right here because the hydrogen will have added here. But here's what you have to consider. If you have a molecule with a secondary carbocation near a tertiary carbon, you will get a carbocation rearrangement. You're going to get a hydride shift. And so even though it looks like the Markovnikov addition will happen right there, that hydride shift is going to happen like so, which means I get my carbocation is actually here. And when bromine comes into attack, it's going to attack right there. That saves me a step because I don't have to do this either. I can go straight from here to here. I don't need any of those steps. So let me show you that I can get rid of these two, even though I thought I needed them, because knowing that I'm going to have a Markovnikov addition that puts a carbocation at the secondary position, I will have a hydride shift. So I may as well take advantage of that and use the hydration reaction that will involve the carbocation rearrangement, which means I'm just going to use acid and water So instead of the HBr, I'm just going to use H2SO4. And that means instead of a bromine coming in, it's going to be a water coming in, and that'll give me the alcohol. So, hey, that turned out to be a lot easier than I expected. H2SO4 in H2O is going to go straight from, no, not there. It's going to go straight from here to here. H2SO4 and H2O. And there we go. We are good to go. This reaction turned out to be easier than I thought. Question. The carbocation will shift into the ring. Yes. I like your handle. Zero motivation. Well, hopefully this session gives you a little bit of motivation, but you are absolutely correct. So once the carbocation is here, then water will attack. It'll get deprotonated, and I have my alcohol ready to go. Yeah, there you go. I like that. All right, so that is the Orgo 1 version. Now let's try this, the Orgo 2 version. Once again, where I have my starting molecule with an alcohol. I do not want to draw that ring a million times, so let's just do that. Somehow, some way, I want to turn this into a molecule that still has an OH at that same carbon on the ring, but it also has 2 carbons added, somehow squeezed in there. Orgo 2, this is a lot easier. Anytime you recognize this pattern, this is a different Grignard pattern. Here's what I want you to look for. If you have a carbon and the carbon has an OH and it has a new R group, that was a Grignard attacking a carbonyl. So let me draw this in a way that I can make this a lot more obvious. If this right here is my OH and this is my new incoming carbon, that OH had to have come from a carbonyl. Not had to. This is the best way, in my opinion, to do it. And this right here, break the bond right there and put a Grignard. Make this right here a Grignard. That did the attack. As soon as you see this, you know exactly where to go. If this right here had to be a carbonyl, then the very next step has to be to turn it into a carbonyl. That's a one-step reaction. That's actually quite easy. I turn that into a carbonyl, into a ketone, and then I attack the ketone with a Grignard. Good to go. That is it. So what are my reagents? The first one is a redox reaction, which may also show up in your alcohol chapter. Because I'm going from a secondary alcohol to a ketone, I can use whatever I want. So for example, I don't know why my mind just went blank. I can use PCC. PCC for a primary alcohol will stop at an aldehyde, but for a secondary alcohol, it goes to a ketone, and therefore it doesn't matter. Then I bring in a Grignard. I need just these 2 carbons. So I will bring in a 2-carbon Grignard. We'll put an MgCl on it. That is step 1. Step 2, we need water or acid, mild acid, because this will turn into an O- when it gets attacked, right? The Grignard attacks here, kicking that up, making that an O-. And if I leave it that way, it's negative. So I bring in acid to protonate it, and there we go. That is the product, a 1 intermediate reaction. Did that turn out to be easier or harder than you expected when you first saw the question? This right here was a Grignard reaction, which I want to say 90+% of students learned that in Orgo 2. I learned it in Orgo 2. I am working with a student now who covered it in Orgo 1. I don't know what her professor was thinking, but she had it in Orgo 1. All right, let's go to, let's go to this problem next. Say you're given a molecule that looks like, how does it look? Hang on, I'm trying to make this up on the spot. That looks like this. And somehow, some way, you want to turn it into a molecule that looks like this. Looks drunk. Let's try drawing that a little bit better. Yeah, let's say that's close enough. What do you think? Easy, medium, or hard? Sarah, you are very welcome. Hopefully it feels a lot more doable after tonight. Well, let's see how we get through this problem first and then decide if it's more doable. I'm currently watching the 17 videos and your alkene mechanisms. Thank you. I'm honored that you are taking the time to go through them, and I am very happy that they are helping you. All right, so if this looks like an easy question, it's kind of a tricky question because it looks so simple. What is the same? Everything. What is different? Question 2. That I turn an alkene that is trans into an alkene that is cis. Question is, what reaction will turn a trans alkene into a cis alkene? If you don't remember that reaction, it's because there is no such reaction that goes from a trans to a cis. And so we have to take a step back and consider, if the starting molecule is not in question, what reaction do I know that will give me a cis alkene? I know that I can create a cis alkene from an alkyne where we have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. So if I have an alkyne with a triple bond between 2 and 3, just like I have with my alkene, then I can do a partial reduction specifically under conditions that will give me the cis alkene. Which then brings up the question, how do I go from an alkene to an alkyne? Would be a trick question, except we've already done it. So hopefully you remember that we don't go straight from the alkene to the alkyne. We first go to a dihalide. For example, let's use Cl and Cl. Then we do a double elimination to get the alkyne. And hopefully, if you found this question difficult before, seeing it again now, if you're thinking, this is so easy, I just saw it, that is my goal with synthesis. The more you can see these patterns, the more you can recognize that reactions are similar and all I have to do is change this thing and change that thing, your professor will not be able to come up with anything new to scare you. Speaking of doing all the practice, as a reminder, put live notes in the comments for a copy of everything that I'm drawing today so you don't have to copy it down. I have a free synthesis worksheet available on my website. Sorry, not available on my website. Just put worksheet in the comments and I'll give you a link to that. And the brand new Orgo pre-finals assessment, to get a sampler of that, put final in the comments and I will link you that. Yes, even if you're watching the recording, I make sure to go through, my assistant helps me go through all the comments and drop all the links when students ask for them. So put those in the comments and let's continue. We've already seen how to do this. We just use Cl2 in something like CCl4. Then we do a double elimination, which would be, nope, that's not what it would be. It would be NaNH2 in NH3, which is not followed by H2O in this case because it's not terminal. There's a carbon group here and a carbon group here. So there's no additional elimination. The only thing I'm eliminating are 2 hydrogens and 2 chlorines. So we grab an H and a Cl, an H and a Cl. We get the double elimination. We get the alkyne. And then to get the cis, specifically cis version of the alkene, I'm going to use H2 in a Lindlar's catalyst. And that's it. That's how I get my product. I hope, and let me know if that's the case, that this was an easy question based on what we have been looking at so far. So let's see how well you know your patterns by doing this next one. So we'll start with a molecule that has a chlorine on it. And we'll end with a molecule that has a chlorine on it. Okay, so here's the problem. Let me know if this is easy, medium, or hard. And these questions are similar to what I have on the worksheet, so you have an idea of what kind of tricks to look out for, but then you get a lot more practice on it. Where do I start? Well, first thing I'm going to do is ask myself the two questions. Question number one, what is the same? Question number two, what is different? What is, wait, did we already do a problem like this? I feel like we did. Yeah, we can do this. This is similar enough, or should we make it harder? Let's go with, let's change this up. Yeah, let's keep the chlorine and make this an aldehyde. There we go. Now it's a different problem. Hello. There we go. I see hard and easy. So let's see if we can figure out which one this is. All right, so what is the same is I have a 6-carbon ring. And what is different is that I have a chlorine that somehow changes to +2 carbon and an aldehyde, which is on one of the 2 carbons. We have a lot to do here. We have a chain elongation, and we have to get an aldehyde onto the molecule. So let's ignore the starting molecule for a moment and just look at the product and think about what we can possibly do here. What reaction do you know? Forget the starting molecule, just in general. What reaction do you know that will give you an aldehyde on a molecule? So I'm thinking I can do oxidation is probably the first thought that comes to mind if I have a primary alcohol. But I also know that I can take an alkyne and do an alkyne hydration that will give me an enol and then ketoenol tautomerization. But if I'm thinking how to get the aldehyde on there, specifically in the context of following chain elongation, then if I'm thinking Orgo 1, the only chain elongation I know is adding an alkyne, I know that I can turn that alkyne into an aldehyde, and that's it. I'm off to the races. I know exactly where to go. If I go one step back, just grab part of the skeleton. If I go one step back, I know that this will have come from an alkyne, and the alkyne will get turned into an enol and then ketoenol tautomerization automatically. So then I can look at this as a new problem. How do I go from, oh, that turned out to be easier than expected. How do I go from here to here? Very simple, an SN2 reaction. So if I have an SN2 reaction followed by an alkyne reaction, that's it. It's 2 steps. It looks so scary, but it's just 2 steps. Step 1 for SN2, it's chain elongation. I bring in Na, and then I have it here as a CCCH. Step 2, if I want the aldehyde, that is the same as doing an anti-Markovnikov hydration, except with an alkyne. So hydroboration for an alkyne, you're more likely to see B2H6 rather than BH3 in THF as step 1. Step 2, NaOH and H2O2. Now, the way I showed it to you, I went straight from the alkyne to the aldehyde product. But in reality, what you're going to get is a molecule, an intermediate that has only 1 pi bond rather than 2. So 1 pi bond got broken. You got an alcohol right there. And what you have here is an alkene plus an alcohol. That is how we have the enol. And the enol will undergo ketoenol tautomerization automatically. It is not isolated as an enol. It automatically tautomerizes to give you the aldehyde. And that is why I was able to show it in 1 step. But some professors do want you to show the intermediate. So you'd have to draw it out like this, put it in brackets and put KET to show it's an intermediate. It does not get isolated, but this is part of what you're going to see along the way. Let's look at this reaction again with the lens of Orgo 2, because in Orgo 2, most students are not used to using the alkyne anymore. So let's see how we can do this differently. Remember the Grignard pattern. If you have two carbons where one has an alcohol and the other one has a new carbon chain on it, I told you that comes from an epoxide. If you have something that looks like it could have come from an alcohol, it still has that same pattern. The carbonyl came from an alcohol, and this right here was added via Grignard. So before I look at the whole thing, I'm just going to look one step back and say this. Oh, I forgot I copied all that. I'm going to look just one step back and say that this came from having this right here with an alcohol right there. That came from an epoxide. And that means that if I have the epoxide here, this is where I break it. That right there was my Grignard. And so now I know my first step here is to turn this into a Grignard, where if I add magnesium in ether, the Mg will insert itself right there. And now I have a Grignard. And all I have to do is attack the Grignard. Well, not attack, add in an epoxide for the Grignard to attack, and I'm good to go. So I have my first reaction is a Grignard. This is the Grignard formation. The second one would be either the epoxide chapter or the Grignard chapter, depending on how your book has it. The third one is a redox reaction. And we are good to go. Let's go through the reagents real quick. For the first one, to make the Grignard, I use magnesium and ether, for example, ET2O. For the second one, I've already shown you the epoxide. That is step one. But step two, I need to add some water or acid to protonate it. Once I have the alcohol, which will be on the primary carbon, I need to oxidize it partially. Otherwise, it'll go all the way to a carboxylic acid. And so I use PCC. And there you go. That's my final product. Right. I know this is a lot to process, but as I said, I've got you covered. Just put live notes in the comments and I'll send you a copy of today's session notes. Worksheet in the comments for even more practice on synthesis and multi-step reactions. You'll also get a heads up for the upcoming live streams, which I'm going to do quite a few more before finals. And then finals in the comments for a copy of my brand new Orgo 1 pre-finals assessment. You'll get a sample of that, 15 questions to test you on just all the different pieces in Organic Chemistry 1.